Hey everybody, welcome to today's lecture. We're still on complexity, which we were on last week. What we're going to talk about this week is how do we prove some complexity results. So in the introductory lecture, we said that we're not going to just take things on faith like we did previously. We're going to make sure that any result we talk about, we can prove. Okay, so in the last lecture, we introduced things like big O notation and theta and omega, but we were kind of hand wavy about them. And what's interesting to me is how do we go about proving the results that we talked about in the last lecture? Okay, so the first thing I want to talk about is set membership. So if you remember from the last lecture, we talked about the fact that big O f of n or theta f of n or omega f of n are sets. Right? They're sets of functions that have some property. For instance, big O f of n is the set of functions that don't do worse than f of n. Okay? So let's say we had some algorithm. It doesn't matter what that algorithm is. And you did hierarchical decomposition like in the textbook. And you ended up with some function representing the time growth of this function as its problem size increased, and the function is f of n equals 3n squared plus 2n plus 6. Okay, so n is the problem size, f of n is the time. Now, what you want to decide is what complexity class the function is in. Now, if you look at it, 3n squared plus 2n plus 6, you probably go, hey, maybe that's theta n squared. Okay, because it looks like it might be. But how would you prove it? Well, if you want to know whether f of n is an element of theta n squared, you can think about the definitions that we had for the complexity classes, right? So if you've got f of n, which is in theta n squared, that would mean that f of n is in big O n squared and f of n is in omega n squared. And if both of those conditions hold, then f of n is in theta n squared, right? That's just directly from the definition. So let's separate it. If we want to know if f of n is in theta n squared, we can first check if it's in big O n squared, and then separately check if it's in omega n squared. Okay, so using the definition of what big O n squared is, we'd say that f of n is in big O n squared if there is a Cn and n naught such that f of n is less than equal to Cn squared for all n greater than equal to some n naught. Okay, now the really cool thing about trying to prove something like this is whenever it says there exists, whenever a statement says there exists and you're trying to prove that the statement is true, you get to pick the C and the n naught. Okay, whenever there's a for all, like that for all n greater than equal to n naught, you don't get to pick it. So you can kind of picture a proof as like an adversarial conversation. Okay, it's you against someone else. And you're trying to prove that the statement is true, and the other guy is trying to prove that he's not even trying to prove that it's not. He's trying to prove that we don't know or it's not, right? He's trying to prove that you're wrong, basically, and you're trying to prove that it's true. Now, in that circumstance, because I want to prove that it's true and there exists there, I get to pick the C and the n naught. But the other guy gets to pick the n, okay? So what we want to do is pick a C and an n naught such that 3n squared plus 2n plus 6 is less than or equal to Cn squared. Because if we can do that, then the statement is true, right? Because that is just another way of writing the statement. I've just changed the f of n to 3n squared plus 2n plus 6. Okay, now remember the whole point of doing any of this is to do complexity analysis, right? N is a problem size. It's the number of elements in your data. Now that number of elements is never going to be negative. Okay, you can't try and sort -3 numbers or something. So we know n is positive. And if n is positive, we know that n must be less than n squared, right? I mean, this is true for all numbers except 1. So pretend there's an equal to there and then it'll be true. So if n is less than n squared, we know that 3n squared plus 2n plus 6 is less than 3n squared plus 2n squared plus 6n squared, right? Because basically all we're saying there is that n is less than n squared and 1 is less than n squared. okay? Which means that 3n squared plus 2n plus 6 is less than 11n squared. Okay, so you can quickly see, if you just take this disconnected statement that's equal to this one, you can say if we picked c equal to 11 and n naught equal to 1, then we know that 3n squared plus 2n plus 6 is less than or equal to 11n squared for all n greater than 1. Okay, so that means we've managed to verify that the statement over here is true, where f of n is 3n squared plus 2n plus 6, and it's less than or equal to cn squared if c is 11. Okay, so if we do that, we know that f of n is an element of O(n) squared. Okay, now as a, this is now going back a step, and we're saying that, okay, we've now proven this part. We've proven that f of n is an element of O(n) squared. We've still got to prove this one, that f of n is an element of omega n squared. Okay, now what would it mean to say that it is an element of omega n squared? Well, f of n is an element of omega n squared if there exists a cn and n naught such that f of n is greater than or equal to cn squared for all n greater than n naught. So it's the same as the other definition, except with a greater than rather than a less than, right? Now the point is, because of this there exists, we get to pick c and n naught, right? Now we obviously not going to pick the same c as we picked the last time, because that c showed that f of n was less than or equal to cn squared, right? So we want to find a different c and n naught that makes 3n squared plus 2n plus 6 greater than or equal to cn squared. Okay? And this one's a bit easier, because if n squared is positive, I mean n squared is always positive, right? So it doesn't matter. Then we know that 3n squared is greater than n squared directly. Okay? And 2n plus 6 is positive, right? There's no way 2n plus 6 can be negative for a positive n. Okay, so that means that 3n squared plus 2n plus 6 is greater than or equal to n squared directly. Okay, so that means I just have to pick c equal to 1 and n naught equal to 1, and that'll mean that 3n squared plus 2n plus 6 is greater than or equal to n squared, and it'll satisfy this equation. So f of n is an element of omega n squared, and we already know that it's an element of big O n squared, so f of n is an element of theta n squared. Okay, that may have sounded like a bit of a mouthful, but fundamentally, because we know that theta is the intersection of big O and omega, if I can prove that there's some function in O and in omega, then it must be in the intersection, right? Because that's just how we define an intersection. So it's in theta, okay, which is what I was trying to prove the whole time. So this was quite cool, because purely given the definitions, we could prove that that a function that we had was in a particular set or a particular complexity class. Okay, and this example made it look fairly easy, and sometimes it is, okay, but sometimes it's not. So we also have an alternative. There's another way we can do this using limits, and I like this method a little bit more because it feels a bit more meaningful, right? So this way that we did here was nice and straightforward from a mathematical perspective, right? It was very nice to be able to just plug in the definitions and just go, right? But it was harder to figure out what it meant. It was harder to have some intuition about what's happening there, okay? So I would generally suggest using this alternative method, using limits, right? And it's fine. You can do either one. There's nothing wrong with it. As long as your proof is correct, you can use limits or use the other method. So let me go through how we'd think about using limits. So the whole point about using limits, the way we can understand it is that when we talk about these complexity classes and something being in some set, what we really care about is how the time taken grows relative to the problem size, right? So we can restate our definitions. We can say big O f of n is an upper bound. So what we're saying is the functions in this class don't grow faster than f of n. Okay, meaning the time taken doesn't grow faster than the function that defines the complexity class. Okay, so that means they do no worse, which is exactly what we wrote in the original definition, but we've changed this now to be written in terms of the growth. Okay, so remember, because the function itself represents time, growing faster is a bad thing, right? We don't want the time to grow. Time growing means we are taking longer. With omega being a lower bound, we're saying that all functions in this class grow no slower than f of n. Okay, meaning that their growth is worse than f of n. Okay. With theta, we're saying all functions in this class don't grow faster or slower than f of n. And again, remember, we're ignoring constant factors and we only care about very large numbers. But the point is, we've reframed this to talk about the growth of the function. Now, let's look at how we can use limits. So think about the ratio f of n over g of n. This is for any two functions, right? If you've got two functions, f of n and g of n, if I take the ratio, right, I expect a certain property to hold. If f of n grows faster than g of n, what would you expect the limit as n tends to infinity of f of n over g of n to be? Now look at these two. If f of n grows faster, you'd expect the numerator to be getting bigger than the denominator, right? So over time, as this thing just grows faster and faster compared to this one, you'd be expecting this ratio to increase, right? So which means you'd expect eventually, in the limit, you expect it to be infinite. Okay? So if f of n grows faster than g of n, we'd expect this limit to be infinite. Makes sense, right? Similarly, if the denominator grows faster than the numerator, so if g of n grows faster, you'd expect this quantity here to be getting bigger and bigger and bigger and bigger and bigger. And so eventually in the limit, you'd expect the limit to be 0. Okay, now let's do an example. We had this function, f of n equals 3n squared plus 2n plus 6, and we were trying to prove that it was an element of theta n squared. Now let's look at how we can do it using limits. So, is f of n an element of theta n squared? Remember, by the definition of theta n squared, that means that f of n is an element of big O n squared and f of n is an element of omega n squared. So we've got the same start we had when trying to prove this result using the definitions. Now, let's look at it. So is 3n squared plus 2n plus 6 an element of big O n squared? I've just pasted the definition from a few slides ago. O n squared is an upper bound. All functions in this class grow no faster than n squared. Okay, so let's look at this ratio. 3n squared plus 2n plus 6 over n squared. Okay, this is just the ratio of these two functions. Okay, let's take the limit. So if I take the limit as n tends to infinity of 3n squared plus 2n plus 6 over n squared, I can do a bit of mathing and I get, that's a word, right? I can math things. So when I'm doing that, I'm mathing, aren't I? But that's equal to the limit as n tends to infinity of 3n squared over n squared plus 2n over n squared plus 6 over n squared, right? That's just that thing rewritten. And that limit, it's easy to see, is 3. Okay, so that's great. I've gotten the ratio of these two functions. I've taken the limit as n tends to infinity and I've gotten 3. Now, if 3n squared plus 2n plus 6 grew faster than n squared, what would you expect this limit to be? Remember, we said if the numerator grows faster, we expect the limit to be infinity. Okay? So if this top one grew faster, we'd expect the limit to be infinity. Is it infinity? No, it's not. It's 3. Right? So since it's not infinity, this doesn't grow faster than this. Okay? So 3n squared plus 2n plus 6 grows no faster than n squared, which is basically our definition of big O n squared. Big O n squared. So we can say that 3n squared plus 2n plus 6 is an element of big O n squared. Okay, does that make sense? So I like this one because there's some intuition about what it means, right? When we say 3n squared plus 2n plus 6 is an element of big O n squared, it means that 3n squared plus 2n plus 6 doesn't grow faster than n squared, meaning it's not worse than n squared. Like I said, I like it because it's meaningful. Okay, but that took us halfway there. We also have to prove that 3n squared plus 2n plus 6 is an element of omega n squared. Okay? So just pasted the definition of omega n squared the same as I did for big O, and it's a lower bound. It says all functions in this class grow no slower than n squared. So let's look at the same ratio, right? We know what the limit is already because we worked it out. But in this case, if the denominator grew faster, right? So meaning if this top one grew slower, you'd expect the limit to be 0 because this number would be getting bigger and bigger and bigger, and this one wouldn't be, and so you'd get 0, right? The limit would eventually become 0. But it's not 0, it's 3. And since it's not 0, we can say that 3n squared plus 2n plus 6 grows no slower than n squared. And that's basically the definition of omega n squared. So we can say 3n squared plus 2n plus 6 is an element of omega n squared. And since we already know it's an element of big O n squared, we can say 3n squared plus 2n plus 6 is an element of theta n squared. Okay. Now, in practice, this was just to show you a good explanation of why it works, and I would advise you to keep that explanation in your head. In practice, what we can do is we can say, well, if I want to prove that it's an element of theta n squared, all I have to show is that it's not 0 and it's not infinity. So I can do it in one step. I don't have to take 4 slides like I took here. You know what I mean? If the limit is 3, then it's already an element of theta because it's not 0 and it's not infinity. Okay. On the other hand, if it was 0, then it's only an element of big O because it's not infinity, but it's not an element of omega because it's 0, right? So you can do this a lot quicker using limits. Now, one of the reasons I'm emphasizing this so much is I find that when you try to memorize this as a student, you're going to get questions wrong. You're gonna infer the wrong things, and you're just gonna get it wrong when answering test questions. Memorizing this is the wrong thing to do. What you want to do is sort of memorize the logic, right? Because if you have the logic in your head, then if you have some confusion over what this limit should be, you can actually reason it out. You can go, well, if that one grew faster, I would expect this to become infinity, so it doesn't grow faster than that, so it's in big O. You know what I mean? Like, you don't have to, you can kind of logic out what it means. And I think this is true of complexity in general, that the more you try to memorize, the more you're going to get stuff wrong. You kind of want to memorize the principles, but you want the actual mechanics of it to be something you can reason about at each time you get asked a question. You know what I mean? Okay, so, but that was about proving that some function which we'd already decided is the complexity of our function is in some class. There's also another thing we should try and think about, which is, what do these sets look like? What functions are in them? And you've dealt with some of this in the TUT, in the quiz that you guys had to do. But here's an interesting question. Look at O(n) squared and O(n). Right? These are two separate sets, but they have some functions in common. Now, the question I'd put to you is it true that every function in big O(n) is in big O(n) squared? Like, that seems like they should be, right? Because if I'm upper bounded by the function n, then I'm definitely upper bounded by n squared, right? If my function is below n, then it must be below n squared somewhere, right? So if I'm not violating the condition that I don't grow faster than n, then I also won't violate the condition that I don't grow faster than n squared. That sort of makes sense, but can we prove it? So let's think about this. Let's try to prove that big O of n is a subset of big O of n squared. Okay, if we can prove that, then it means that we're getting to some intuition of how this stuff works. Okay, so let's look at this. If I want to prove that this is a subset, and I'm not sure how many proofs you guys have done of this form in math, but probably a lot. If I want to prove that something is a subset, what I want to prove is that every item that's in the first set is in the second set. A common way to do that is to pick an arbitrary item of the first set and put no restrictions on it. So that it's functionally like a representative of every item in the set. Okay, so that's what I'm going to do. I'm going to say let f of n, one particular function, be an element of big O(n). but I'm introducing no restrictions on f of n. So it can be any function in big O of n. And any result I prove will be true of all f of n's, if that makes sense. So first thing is, if f of n is an element of big O n, then I know that there exists a Cn and n naught such that f of n is less than or equal to Cn for all n greater than or equal to n naught. Okay, I know that because that's the definition of big O n. So that wasn't me doing anything clever. I just basically took this big O n and replaced it with its definition. Okay, but we know n is positive. So n must be less than or equal to n squared. Okay. I guess that's not really true for fractions, I guess, but we know that n is greater than or equal to 1, right? Because remember, it's meant to represent the quantum of data you have, right? So you can't sort half an item, you sort 10 items or something. Okay, so n is a positive integer, basically. So for positive integers, we know that n is less than or equal to n squared. Okay? And so if we look at this statement here, we know that f of n is less than or equal to Cn. But it must also be less than or equal to Cn squared, right? Because n is less than or equal to Cn squared. So we can write it out like this. If I then just take out this middle one, I get that f of n is less than or equal to Cn squared for all n greater than or equal to n naught. But this looks familiar. This is basically the definition of f of n being an element of big O n squared. Okay, so I started off with f of n being an element of big O n, and then I've ended up with that implies that f of n is an element of big O n squared. And I didn't put any restrictions on f of n, so it's basically every element of f of n, of big O n. Okay, so that means if f of n is in big O n, it's automatically in big O n squared. Okay, which means that big O of n is a subset of big O n squared. So we proved this. What would we do if we had to prove that big O n was not equal to big O n squared? So it's a proper subset. And there's no equal to there. How would I do that? How would I prove? So if I already know this, how would I prove this? Well, the only difference is whether they're equal. Okay, so if I want to prove that these two sets are not equal, all I have to do is find one element that's in one set and not in the other. And if you look at these two, if you had to pick one element that you'd say is in one of the sets and not in the other, what would be the easiest one? Well, the easiest one would be to choose the function n squared itself, right? Because I can see that n squared is going to be in big O n squared. It's going to be straightforward. And I believe that n squared is not going to be in big O of n because this is the set of functions that are upper bounded by n, and n squared is, worse than that, so it's above it. So we wouldn't expect to see n squared in here. Now, if you had to prove that these sets were not equal, you'd let f of n equal to n squared, and you'd prove that f of n was an element of big O n squared, which you could do using limits, and you'd prove that it's not an element of big O n, again using limits, right? So if you wanted to use the limit, I'm not going to do it here, but I'd advise you guys to try it because I think it's a good exercise, and it's certainly one you'll have to do in an exam, so you may as well do before the exam. If you have f of n equal to n squared, and you want to prove that it's in big O n, you just take the ratio. You take n squared over n, and you take the limit as n tends to infinity. And if the limit is infinity, then it means the top one grows faster than the bottom one. So n squared grows faster than n, which means it can't be in big O n because big O n is the set of functions that don't grow faster than n. Okay? Okay, I guess I mostly did it, but more by saying it than by actually writing it down. So, so on the whole, I think the key and what I want to just get across here is that this all looks like math, right? But none of it is really super abstract. And what I'd advise you to do is try and keep it from becoming super abstract, right? The right thing to do here is to just continuously be translating things in your head, right? When you see something like this, looks like math, then you go, okay, well, let me try and say that in English. What I'm trying to prove here is that the set of functions that don't grow faster than n contains only items that are also in the set of functions that don't grow faster than n squared. And the set of functions that don't grow faster than n squared has at least one item that's different from the set of functions that don't grow faster than n. Okay, that was a bit of a mouthful, but I think it helps illustrate. So, similarly in the previous set when we were talking about is 3n squared plus 2n plus 6 an element of big O n squared, what we're trying to say is 3n squared plus 2n plus 6 in the set of functions that don't do worse than n squared asymptotically. Okay, and if you keep translating that sort of thing in your head, it becomes much easier to figure out what's actually happening. Okay, I hope that was useful. Follow along in the book if my explanation is bad, and there's probably tons of very good explanations on YouTube as well. Thank you.